meeting that you're going to be at, although I'm planning on dropping in occasionally just to see what's going on, but whatever. The last formal, faculty meeting, department meeting, and I interrupted her and I said, and so what you'd like is for me not to say a word, just to be different. She said, no, you can do some demonstrations if you'd like. I went, whoa, demonstrations. So anyway, I'm going to show you a bunch of demonstrations. This is stuff that we do with the kids. It ranges from really simple to a little bit more complicated.
Hi, sorry.
It's all right. You missed the preamble, but it's okay.
We had
I'm
to
sorry,
You say.
So anyway, as I was starting to say, when I say I mean basically Richard and I do, pretty much the same stuff. So this is Richard too. We do demonstrations in an attempt to get the kids to number one, show them stuff that they wouldn't expect. So the perfect demonstration is to ask them, what do you think is going to happen? And then when they see what happens, they realize, oh my God, that's not what happened. And then you get into talking about the physics, and by the time you get done, hopefully they conclude, oh well, that's probably what should have happened. So, and the demonstrations can be really simple, or they can be more complicated. So a really simple one is this. So this is just an axle, a couple of wheels. There's string. The string goes underneath. Okay, it goes underneath. I'm putting it down on the table, which unfortunately is not flat, so it's going to roll a little bit. Stop rolling. Stop. Stop. Okay. What I'm going to do is I'm going to take the string and I'm going to gently tug on it. And the question is it going to roll that way or is it going to roll that way? How many think it's going to roll that way?
I think the thing that's not going to happen is
don't
going to happen.
even start.
It's the opposite of what you would
You
always
just
think.
piped that out there. How many think it's going to roll that way?
Which
How
way
many,
are you
how many
going
aren't? How many aren't thinking? What the hell? I only have two people who are. I'm going to pick the string up. I'm going to pull it gently. I want to know whether you think it's going to go that way or that way. Just give me a gut reaction. How many think it's going to go that way?
Wait, horizontal to the
Don't
flexors? Or
fuss with me. I'm going to pick the string up. I'm going to pull it.
Be a 12th
I want to know whether you think it's going to go that way or that way.
Left or right?
Okay, I say that way.
How many people think it's going to go that way?
Feels
How many think it's going to go that way? Okay, so the majority think it's going to go that way. Right. So I'm going to go ahead and I'm going to pick it up. And oh, look at that.
you pull up.
inertia.
Now, I don't want you folks to feel bad. So let's try it again. How many people think it's going to go that way?
Which way are you going to pull the string?
I'm just pulling it out. I'm just pulling it out.
But last time you pulled it up.
No, it was already.
Yeah, you did.
How many think it's going to go that way? How many think it's going to go that way?
I'm sticking with this.
Very good. Okay, so I'm going to go ahead and give it a little tug.
Yeah.
Oh, look at that. It went the other way. So the reason why I use this is because it gets the kids talking about what's called torque. So if you want something to angularly accelerate, you have to apply a torque to it. And basically what's coming down to it is the string is what's providing the torque. And when it's at this angle, the torque is tending to make the body want to angularly accelerate that way. And when the string is at this angle, the torque is making the body tend to want to angularly accelerate that way. So you get the kids talking about this idea of torque. You do the math, you do all that, but it's a way of kind of nudging them into thinking about this. So that's one way we use demonstrations, is to try to get the kids, involved with whatever. One of the ways we do demonstrations is to just show them kind of amazing stuff. So if you have a kid on a swing and you push and you wait for a while and then you push and then you wait for a while and then you push, basically what you're animating is this idea of resonance. So the force that you're applying, the frequency of the force that you're applying matches the natural frequency the swing is willing to oscillate at. And assuming that you push at that frequency, the amplitude will get bigger and bigger and bigger and bigger. If you push at a frequency that isn't that natural frequency, then you get mush. So you push, and then the kid goes out, and then you run up and you push when the kid's right here, okay? You're not pushing at the right frequency, and all hell breaks loose. Okay. So, right. So it turns out that there's this other phenomena it's related to resonance, in which you get waves moving in two different directions, and they superimpose on one another. And under normal circumstances, they'll do it in a way that's kind of chaotic. But if the force that's driving the system, and I might add, the system we're going to be looking at is that string back there or that rope back there. So I'm going to be oscillating this rope. I'm going to be applying a force. Well, you might want to move it. So I'm going to be applying a force that's generating a wave. And the wave will propagate down the string, and it'll hit this end, and it will bounce, and it will come back. So what you end up with are waves going this way and waves going this way. And they'll superimpose on top of one another. If the frequency is just right, if it matches one of the natural frequencies that this system can oscillate at, you'll end up with what are called standing waves. And standing waves are very orderly waves that have characteristics that are sort of unusual. So what I have here, this is just a drill. I actually don't have kind of angle right. Hold on a second here. I'm going to use this just here. Come on, I'm using a drill to generate the oscillation. So it's going around, but basically it's creating a wave. And I have this is called a variac, and basically it allows you to vary the voltage of the drill from 0 to 120 volts. Turns out there's a DC motor in drills, and because that's the case, the voltage dictates the rotational speed. So if I bring the voltage up just a little bit, it rotates, and you can see it's kind of mushy. Okay, it's sort of bouncing all over the place. But if I hit one of the natural frequencies, I'll get a standing wave. So this is what's called an n=3 standing wave. And what's actually standing on this is energy. So there's no energy here at all. And remember, this is the consequence of waves going this way and this way, superimposing in this very orderly way. So you can literally put your hand around here, assuming you get the right frequency, which I don't quite have. You'll see how it's going about. It means I don't have the right frequency, but you can fuss. So the higher the spin rate, should say, you get a different frequency, different standing rate. Higher. A different standing rate. So you'll see how it goes and then it collapses because I'm not dead on the frequency. But you can take it all the way up. It's a slow down. So anyway, there's math involved with this, and the whole idea is to present the concept in general, and then talk about the math, and then do the lab. And so in the old days, when we had more time, we used to do this lab. The honors folks did, and they would have to predict, given the information having to do with how to figure out the natural frequency. There's kind of like a technique to doing this. They had to predict what frequencies would make a n=3, n=4, and n=5 standing wave. And then, because we needed to know what the frequency was, it was actually quite cool. Drills don't have counters on them. So trying to figure out what the frequency is hard. So I figured out a way of using a strobe light. And so we would get the strobe and we'd fuss with the strobe until the strobe was flashing at the same frequency that the thing was going at, which would make it look like it wasn't moving. And then we would take the strobe and stick it against the solar cell, which was attached to an oscilloscope. This is an oscilloscope. It would show the waveform of the flicker of the strobe, and from that, off the oscilloscope, you could figure out what the period was, and from that, you could flip that over and figure out what the frequency was. So it was a very cool lab. The kids had a grand time with the strobe. You know, whatever. But anyway, I use it as a demonstration now. We really don't have the time to do it as a lab, but that's the idea. You mess around with the math, or you mess around with the concepts, then you mess around with the math, then if you're lucky, you've got some kind of demonstration that will allow you to show. Let's see, what else? So it turns out, oh, nuts. Richard, do you know what happened to the magnet? Oh, never mind. So, thank you. I have to say, I'm constantly unable to find things. And I just go into Richard's office and say, do you know where the so-and-so is? And he says, no, let's go look. And he walks in and just says, here it is. Just hands it to me and then walks in. This happens all the time. I like to say that it has to do with OH, but it doesn't kind of been that way in my entire life. So anyway, it turns out that if you have a coil and you have a magnetic field passing through the coil, it generates what's called a magnetic flux. If the magnetic flux changes, and you can do that a whole lot of ways. You can turn the intensity of the magnetic field down. You can rotate the coil. A lot of different ways of doing it. If the flux changes, it will induce a current in the coil. And that current will generate its own magnetic field. So with that in mind, I have this aluminum pole here. It's actually it's a tube. Okay? It's something that is not magnetizable. This is a magnet. It's not magnetizable, but it is metal, which means that current, you can get currents in it, you can get charge to flow. So if I go ahead and just take this thing and just drop it, okay, gravity takes over, it drops like a rock, with exactly what you'd expect. But if you put it into the tube, an interesting thing happens. So if you just zero in on that section of the tube and think of it as a coil, as the magnet, let's say this is the south pole of the magnet, as the magnet approaches, the magnetic flux through that coil changes. You get an induced current, and as a consequence, you get an induced magnetic field. And if this is the south pole, this side of the coil, due to that magnetic field, will act like a south pole. So as this thing is approaching, you have a south pole juxtaposed against a south pole, and you get a force that's upward that retards. Once the thing gets through, the direction of the current changes. This is a north pole. Okay. This had been a south pole, but when the current changes, now this is a south pole. So when it's on this side, you have a north pole juxtaposed against a south pole, and again, you have a force up. So if I let this thing drop through the tube, it takes a long time to get through because there's this constant force, because you don't just have one coil, you have an infinite number of coils. The entire tube is doing this during the entire time. The consequence is that the thing drops very, very slowly.
How does it eventually break through them?
See what?
Gravity is stronger.
Yeah, gravity. Once it gets out here, then the effect drops to zero pretty quick.
So those are pretty weak induced force then?
Yeah, yes. I hadn't planned on showing you this, but I seem to be talking fast and we have the time, so I will. This is a similar, I made this years ago. There are about 100 or 200 wines of very fine, you know, wire that you and what I have, this one is dropped off, but all the rest of them have an LED attached to the end. So an LED will only let current flow in one direction. So, and also there's a neodymium magnet in this tube. So when I flip this thing over, the magnet is going to fall through the tube. So as it does, as it approaches one of these coils, you get that same phenomena. You get an induced current in one direction, and then when it gets through on the other side, you have an induced current in the opposite direction. Well, the diode will let current flow in one direction, but not the other. So as the thing is flowing through, you ought to see each of the little diodes go blink, 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 blink. So let's try it and see if it's going to cooperate. So you're going to have to look closely. And I might add, I think this is the one that doesn't have a diode attached. So let me see if I can't get it so the diodes are facing. Okay, you ready? Here we go. Yep. See the blinks? Yeah.
Not the other one.
So in one case, the current's flowing. I mean, the current's always flowing in the same direction as far as the diode is concerned. So anyway, my point here is that's the same phenomenon, and you can see it's pretty local, which is what your question was. Is it local? Yeah, it's local. You got to be pretty close before you get enough of a you know, whatever to yeah. All right.
So the aluminum tube is just like infinity of those little spaced out coils.
Yeah.
That's why it
Right.
drops so much faster.
Yeah. Okay, so along the same line, we've got this little guy. So this is not something, this was something that was around, I didn't build this, this is something that was here when I got here. Basically what you're looking at here is it's a wire that's going to get, you know, it's a plug-in, I'm going to plug it into the wall. So you're going to have alternating current. So what alternating current does is current flows in one direction and then flows in the other direction. So basically the charge carriers are jiggling back and forth. This was a very, very long extension cord that had the other end clipped. And then the wires were split, and then they created a coil, and they created a coil, and then they attached it. So this is where that coil is. So basically this coil right here, when it comes out, it attaches to, it's the extension of this wire. So when I plug this thing in, okay, and I push the button, listen. Can you hear the 60 cycle hum? Okay, so what's happening there is the current's going in one direction, then the other direction, then one direction, then the other direction, one direction, the other direction. It's doing it at 60 cycles because that's what you get out of your wall socket, 60 cycle per second, AC. And so you're hearing 60 cycle hum. Anyway, the point is that if you have a coil, you have a current flowing in the coil, it will generate a relatively uniform magnetic field down its axis. And then the magnetic field sort of disperses once it gets outside of the coil. So what I have here is a magnetic field that's going in this direction, in this direction, in this direction, in this direction, because the current is oscillating back and forth. This thing, this outside ceramic thing, is just to reduce friction. Down the axis of this, though, are a whole bunch of steel plates that are glued together. It turns out that steel, it has iron in it, which means it's a magnetizable material. So as the magnetic field in the coil is going doink, 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 the magnetic field going up this axis is going doink, 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 doink. Which means that if you were to go ahead and take basically a rather bizarre coil, okay, which happens to be aluminum, not magnetizable, but again, the charge carriers can move around. If you were to go ahead and put it over here, there would be no change in flux, and there would be no flux. If I push the button, nothing. But if I go ahead and put it here, now you're going to have a change in flux that's set up through this cross section. And that's going to induce a current. It's going to be an alternating current. That in turn is going to generate its own magnetic field. And what you're gonna find is the juxtaposition of this guy's field and this guy's field is always gonna end up being repulsive, which means this thing is gonna wanna go up. So you can do a couple of things with this. One is you can just simply let it get into its equilibrium position where effectively this magnetic force is being counteracting gravity down. Or you can be exotic. You can be exotic, put it down there, push the button, and voila. Okay. So this is the basis of what's called a rail gun. So the military apparently built rail guns years and years ago, and they could use them to throw munitions several miles without any kind of propulsion. It's also the basis for the accelerator on the Superman ride at Magic Mountain. So this is the way that they get the Superman ride to get up to like 100 miles an hour, 80 feet or whatever it is. One of the things I do with the students is I throw these out into the audience so they can see the weight and also the temperature. You have good hands?
No, I don't.
Do you have good hands? Does anybody have good hands? Here. Thank you. Okay, so whatever. Showing it, pass it on.
Oh,
You
it's
gotta
cold.
move fast.
And light.
Yeah, I mean, what I tell the kids is if you hold it for very long, it's gonna warm up just because of your hot little hands. But generally speaking, it's very relatively cool.
So the same way
Okay,
we
throw
do.
back. Or hand it back, whatever.
I have good hands. Oh, I didn't know your computer off for that. Sorry.
Okay, so the reason I do this is that if you do this, all is nice and well. But if you do this, you're generating a really big current in the stuff, and it will heat it up rather rapidly. So this is hot. So when you catch it,
No, she.
I don't want to catch it.
Yeah.
I
No,
believe
you want to
you.
catch it, just
I
touch
believe
it,
you.
just touch it.
A little hot tape.
that was the idea. Here, catch. Okay, so you can see, I mean, the thing that's kind of cool is that you can actually animate the fact that, yes, there actually is a current going on
Yeah.
because the damn thing is hot. And it's really hot, like it's really hot. Anyway, the other thing we can do with this, and we do with this, aside from talking about induced EMFs and all that sort of thing, is you can take a regular old coil with a light attached to it, and you can go ahead and bring it down. You can get power transferred from this coil to that coil without any electrical connection. So this is the basis of what's called a transformer. And there are transformers all over the place. I mean, your computer can't handle 120 volts. So the first thing that power coming into your computer does is it goes through a transformer, which steps the voltage down to like 1.5 volts. So anyway, we talk about transformers. And as I said, this is a demonstration, a very simple demonstration of a transformer. So, okay, so there's that. Occasionally I will show, or I will build something that doesn't turn out to be very useful, but it's kind of novel. And so years ago, the big craze was to lie down on a bed of nails